Hi, my name is Mr. Peck from Ideas Inc. School, and we are here today to discuss about atomic structure. In this chapter, please make sure that you have a periodic table in front of you before we begin. In the periodic table, all the elements are denoted in a Nuclide notation. This is a simple way to show information about an element. In this notation, there are three components. Number 1, the atomic number. Number 2, the atomic mass. And lastly, number 3, the chemical symbol. Please note that some periodic tables may switch the position of the atomic number and mass. Therefore, it is easier to associate the bigger number with the atomic mass and the smaller quantity with the atomic number. Now let's dive into what these numbers represent. The atomic number is the total number of protons found in the nucleus of an atom. The atomic mass represents the total number of protons and neutrons found in the nucleus. This is also known as the nuclear number. Thus, by subtracting the bigger number with the smaller one, we can obtain the number of neutrons. Lastly, in an atom, the number of electrons will always be equal to the number of protons. Let's use the element sodium as an example. Sodium has an atomic number of 11 and an atomic mass of 23. Thus, we can deduce that sodium has 11 protons, 11 electrons, and 12 neutrons. Now let's discuss more about these subatomic particles. Protons are found in the nucleus. These particles are positively charged and have a relative mass of 1 unit. Neutrons are also found in the nucleus. These particles are neutral and have a relative mass similar to that of a proton, which is 1 unit. And finally, electrons are found in the orbitals. These particles are negatively charged and have a negligible mass of 1/1846 units. In the next part of the chapter, we will be talking about how electrons are arranged in an atom. Note that electron orbitals are imaginary rings that surround the nucleus. The first orbital that is the closest to the nucleus can store a maximum of 2 electrons, while the second and third orbital can store 8 electrons each. Please note that the storage capacity of subsequent orbitals will not be explored in this chapter. With this information in mind, let's take a look at the element sodium again. Previously, we are aware that sodium possesses 11 electrons. We will always fill the electrons from the innermost orbital first. Therefore, the first orbital will cap out at 2 electrons, while the second orbital will be filled up with a maximum of 8 electrons. As a result, the third and final orbital will house the last remaining electron. So if we take a look at the electronic arrangement of a sodium atom, it will be 2.8.1. The last digit of the configuration is the most important value. This is the number of valence electrons. This number represents the number of outermost electrons in an atom, and this number will correspond to the group that the element is found in. That is a very quick and easy way to deduce the number of valence electrons of an element. For instance, rubidium is found in group 1 of the periodic table. Therefore, we can deduce, without writing out the entire electronic arrangement, that it has only 1 valence electron. Recall that elements found in the same group will have similar chemical properties, and the reason why is because they all share the same number of valence electrons. In the next part of the chapter, we will be discussing about ion formation. Let's take a closer look at the elements found in group 0 of the periodic table. These elements are known as noble gases. By looking at the electronic arrangement of the first 3 elements in group 0, we will notice that helium has an electronic configuration of 2. Neon has an arrangement of 2.8 and argon will have an arrangement of 2.8.8. So if we pay attention to the arrangement of electrons in those elements, we will notice that these noble gases have all their outermost electron orbitals filled to the maximum. Because these elements have full valence orbitals, we say that they possess noble gas structure. This is a stable configuration, and thus, noble gases are inert and very unreactive. Then how does non-group 0 elements in the periodic table achieve such a stable configuration? They do so by undergoing ion formation. Let's take a look at 2 examples. By revisiting the sodium atom, recall that sodium has 11 protons and 11 electrons. Due to the fact that there are equal number of positively charged protons and negatively charged electrons, atoms are always electrostatically neutral. And when we take a look at sodium's third orbital, we will notice that there is only 1 valence electron in the outermost shell. Since the outermost shell is not full, a sodium atom does not have a noble gas structure. So in order to achieve a full valence orbital, sodium can choose to either lose its only valence electron or gain 7 valence electrons. Because an atom will always choose the path that requires the least amount of energy, sodium will always choose to lose its valence electron to another atom. When this happens, please take note that the number of protons remains unchanged during any ion formation. And now, with 1 less electron, there will be 1 more positively charged proton as compared to the number of negatively charged electrons. Sodium will no longer be a neutral atom and thereafter transform into a charged particle known as an ion. The sodium ion will have an overall charge of +1. This ion will have an electron arrangement of 2.8, and this is similar to that of the noble gas neon. When drawing the structure of ions, note that a square bracket is used to differentiate it from atoms, and the overall charge is always written at the top right-hand corner of the bracket. Please also note that the numeric number of the charge is known as the valency, and only if the valency is more than 1 will it be necessary to write down alongside the charge of the ion. For instance, the sodium ion has a charge of +1. Since the valency of the ion is 1, we can simply denote a plus sign on the top right corner of the bracket. The next example that we will look at is the nitrogen atom. By referring to the periodic table, we can deduce that nitrogen has 7 protons and 7 electrons. And since nitrogen can be found in group 5 of the periodic table, we can infer that it has 5 outermost valence electrons. In order to achieve a noble gas structure, nitrogen can choose to either lose all 5 valence electrons or gain 3 outermost electrons. Because the path that requires the least energy is always prioritized, nitrogen will choose to accept 3 electrons from another atom to achieve a stable configuration. When that happens, there will be 3 more negatively charged electrons as compared to positively charged protons. Nitrogen will no longer be a neutral atom and thereafter transform into an ion with a charge of -3. This ion will have an electron configuration of 2.8, and this is similar to the noble gas neon. When drawing the nitride ion, please note that because nitrogen accepted electrons from other atoms, we will have to denote those electrons with a different symbol from its own. In the last part of the chapter, we will be discussing about isotopes. Isotopes are elements with the same proton number but different number of neutrons. Due to having the same number of protons, isotopes of the same element will have the same electron arrangement and hence the same number of outermost valence electrons. And since valence electrons can be used to depict chemical properties, isotopes of the same element will have the same chemical properties. However, having different neutrons indicates that they will have different atomic masses. Therefore, isotopes of the same element will have different physical properties. Let's take a look at chlorine from the periodic table. If we take a closer look at its atomic mass, we will notice that chlorine has an atomic mass of 35.5. But does this mean that chlorine has half a proton or neutron? That is incorrect. In reality, 35.5 is the average atomic mass of the common isotopes of chlorine. Let's learn how we derive that value. Chlorine has 2 isotopes. One is known as chlorine 35 and another as chlorine 37. These numbers represent their respective atomic mass. As such, we can calculate that chlorine 35 has 17 protons, 17 electrons and 18 neutrons, while chlorine 37 has the same 17 protons and electrons but it contains 20 neutrons instead. And given that a sample of chlorine is roughly made up of about 75% of the chlorine 35 variant, and about 25% of the heavier chlorine 37 isotope, we can calculate the average atomic mass by taking 75% multiplied by the mass of 35, taking 25% multiplied by the mass of 37 and finally summing up the results from both multiplications. If done correctly, we will obtain a relative atomic mass of 35.5. And not to worry, as the percentage composition of isotopes of different elements will be provided in the questions. Chlorine is the only example that requires memorization. We have come to the end of the chapter. Please approach Mr. Peck if you have any doubts. Thank you for listening and have a nice day.